Hey everybody, Jonathan here. In this video, I will be giving you my take on section 6.4, which is all about the physics notion of work. In physics, work is a type of energy. It is specifically the type of energy required in moving objects. Every time an object or a substance gets moved, then there is work energy that had to get expended to make that happen. Now, in the very simple setting where you have an object being moved along a straight line with a constant force being applied to it, then work is defined to simply be the force applied times the displacement of the object. So work is force times distance, as it says so right here. However, in the real world, it's quite unusual to have the force be some constant. What's far more typical is for the force to be changing as the object moves along the line. In other words, at one position, the force will be one thing. At some other position, the force will be something else. Imagine, if you like, a spaceship lifting off from Earth. The force at the surface is going to be greater than the force once it's 100 miles above the Earth because the gravity will be less up there. Now, if the force depends on the position of the object, then we can think of the force as being a function f of x. In this case, we can use the main ideas of calculus in order to figure out the work involved. In order to do this, we're going to suppose that the object is being moved from position A to position B. We're going to divide A, B up into n intervals, each of with delta x, and assuming that the force is a continuous function, we can assume then that the force is going to be pretty much constant on each subinterval. It's going to be approximately constant on each subinterval. So we take a sample point xi star in the ith subinterval, and then we can assume that the force at that point is f of xi star. And that means that the work to move the object across just that subinterval will be about f of xi star times delta x. If we add up the work required to move the object across each subinterval, we'll get to the work is approximately the sum from I equals 1 to n of f of xi star times delta x. And if we take the limit as n goes to infinity, we will get that the work is exactly the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star times delta x, which, by the definition of the definite integral, is the integral from a to b of f of x dx, which, by the amazing fundamental theorem of calculus, we can find this by doing antiderivatives. Now, this lovely formula that the work is the integral from a to b of f of x dx applies when you have an object moving along a straight line and a force being applied at position x equal to f of x. However, there are a lot of other situations where we might want to calculate the work. For example, you might have some type of substance which is somehow split into little bits, for example, water or sand or oil. And a common type of problem is that you're trying to raise this substance up. So for example, maybe you're trying to pump water out of a tank or something like that. The water at the bottom of the tank has to be raised up a lot higher than the water at the top of the tank. So in this case, we can still think about the work required to move a small amount of water at the bottom and a work required to move a small amount at the top, but it's going to be different. So this type of formula doesn't even apply here. You don't have an object moving along a straight line. What you really have is just some substance with different amounts of work required to move different parts of the substance. So imagine that we've got a water basin in the shape of a cone. Now, the way we're usually going to solve these work type problems is we're going to imagine taking the water and splitting it up into horizontal slabs, kind of like so. Now, in each slab, the water particles in each slab are all at about the same height, which means they'll all need to be pumped out about the same distance. And since work is force times distance, we can calculate the distance separately for each slab, and we'll have an approximation for how much work it takes to pump each slab out. Now, technically, each of these slabs is something in mathematics we call a frustum. However, we can make the work of calculating their volume even simpler by approximating them with cylinders. So we can now calculate the work necessary to pump each of these cylinders up to the top And since we'll know the volume of each cylinder and we'll know the distance each cylinder is from the top, we'll be able to calculate the work. So let's try and use these ideas to solve an example. Suppose a water-filled basin is in the shape of a hemisphere of radius 5 meters, and that for some reason the basin needs to be cleaned, so we need to pump all the water out. How much work will it take to pump out the basin? Well, we're going to use that the density of water is 1,000 kilograms per meter cubed. We're going to use that the acceleration due to gravity is 9.8 meters per second squared, and we're going to use that the formula for the bottom half of a sphere is z equals minus the square root of 25 minus x squared minus y squared. So here's a GeoGebra activity I made to go along with this example. So normally the z-axis is vertical, but we also like the variable when we integrate and do things with to be x. So I've made the x-axis be the vertical axis here. And then the y-axis is pointing left and right, and the z-axis is coming straight out towards us. Now the formula for the bottom half of our sphere is y equals minus the square root of 25 minus x squared minus z squared. So what we want to do is imagine having a slab of water a certain height. I made this slider here so you can imagine moving a slab illustrating all the water that's at a particular height. So if we thicken that a little bit, we'll have a cylinder that we need to pump out. To get the radius of this little slab, if we look at the cross section of it in the xy plane, we see that it's just stretching from one side of a circle to another. So its radius will just be the distance from the x value over to the circle. So to get that, we just have to plug in z equals 0. So that means that the radius of the cross section at xi is going to be the square root of 25 minus xi squared. Now if we thicken that a little bit to get a disk, then the width of that disk will be delta x, and therefore the volume will be pi times the radius squared times the height, so it'll be pi times 25 minus xi squared times delta x, where squaring the square root made the square root go away. Now how far up does this guy have to be moved? Well, it's happening at the height of xi, so it's going to have to be moved up a height of minus xi. Here it made sense to me that z equals 0 or x equals 0 corresponded to the surface, so our x values are actually negative here because we're under the surface. So therefore each disk has to be moved up a distance of minus xi. Now, using that the density of water is 1,000 kilograms per meter cubed and the acceleration due to gravity is 9.8 meters per second squared, then minus xi is the distance we're going to have to pump this cylinder out, whereas the force is going to be the acceleration times the mass, and the mass is 1,000 times the volume because the density was 1,000. So overall, we get that the work to pump one of those disks out will be minus xi times 9.8 times 1,000 times pi times 25 minus xi squared times delta x. And now to get the total work, we just have to take the limit as n goes to infinity of that. And that then turns into the definite integral from minus 5 to 0 of minus x times 9800 pi times 25 minus x squared dx. Now by multiplying this x through the parentheses, you can get the actual value if that's something you care about.